All right, so yesterday we started out with this original problem where I said, are these two molecules the same or are they different? And one easy way of telling if you've got an identical molecule is just to name it, right? If it has the same name, it's got to be the same molecule. So in both of these examples, we had 3-methylpentane. And we said this is because single bonds can rotate, the molecules can flop around in three-dimensional space. They're not restricted in terms of their rotation. If you have a double bond, then you do run into restriction of rotation, but we're not going to deal with that right now. We're only dealing with alkanes. And we said that you can draw molecules a variety of different ways. So we're used to seeing bond line notation. However, yesterday we saw examples of Newman projections. They're just different perspectives of the same molecule. So are you looking face down or point on? And we saw with ethane, you can imagine you've got this invisible eye. You look down that first carbon, that's your original cross point, and then the carbon behind it is represented as a circle, and then you can draw your substituents in. And then every time you do a rotation, you go from essentially a staggered conformation, twist it 60 degrees, you drop down into this high energy eclipse conformation, then another 60 degrees, you pop back into that staggered conformation. And so we said energetically, it's kind of like going over this roller coaster where you go up and down in terms of potential energy surfaces. All right, then I left you with this example yesterday. How many of you actually did this? That's good. Some of you might be lying, but that's okay. So we're looking at butane, and I asked you to do 3 different Newman projections. So what I went ahead was I just filled in, we know it's going to go from staggered to eclipse to staggered to eclipse to staggered to eclipse, and then ultimately back to its original form. So let's try to pay attention here. And what I often do when I do these is you can tell I'm only moving the back carbon, right? At least with my arrow pushing. You could rotate the front carbon too if you want, but just stick with whichever one you're rotating. If you're going to rotate the front carbon, only rotate that one, keep the back one static. If you only rotate the back one, keep the front one static. So I'm going to draw in all my front substituents just to keep things easy. So really quickly, just pop all of these in. It's a nice trick on exams to do this too. It'll speed up your exam taking process. So plug all these in. And now if we think about that top methyl group, we know we rotated it 60 degrees to the right. So I'm going to pop that in over here. And then back here, we know the remaining 2 spots are hydrogens. So I'll draw those in. Make sense so far? All right, same idea. I'm going to rotate this methyl group down 60 degrees, so it must be in this position with 2 hydrogens coming off. And then one more notch down here. Rotate it another 60 degrees. The other 2 spots are hydrogens. All right, another 60 degrees. That means we have our methyl group down here, 2 hydrogens right here. And last but not least, we can rotate this another 60 degrees. And have our hydrogens like that. And then last but not least, if we really wanted to, we could rotate it back to that original conformation, right? So we've got 6 different potential conformers. Let's label them as staggered and eclipsed really quick. We know that this first one is going to be staggered. I think it's ED. This one is also going to be staggered. And then this bottom one in the middle is going to be staggered. All of the other ones are going to be considered eclipsed. So just really quickly label those. All right, so now I've got a challenge for you. I want you to determine which of these is most stable, second most stable, third most stable, fourth most stable, fifth most stable, and there can be ties. So I'll give you a minute to work on that. And you can number them if you want. In this case, I would number the most stable one as position 1, and then 2, and then so on. So I'll give you a minute to think about this. All right, so let's try to do this as a class. And what I want to do first is look at the staggered conformations. Staggered conformations almost always are going to be more stable than the possible eclipse conformations, and we talked about that previously. So if we think about the staggered conformations, I've lettered them A, C, and E. Which one's the most stable, A, C, or E? A. And why is that? Rainbow pen. The methyl groups are furthest away from one another, right? So that's first place. It wins the rainbow pen prize. All right? Between C and E, which one do you think's more stable? It's tied. Why? The methyl groups are right next to one another. They're just oriented differently in space, right? In fact, when we look at these, we have a unique way of describing this interaction. People are saying it's destabilizing to have two methyl groups close to one another. This is called a Gauss interaction. It's a Gauss interaction. And then this one's also a Gauss interaction. All right? And in general, the larger those groups are, the closer they get to one another, the more destabilizing it is. We'll take a look at some more complicated examples later, but Gauss interactions are destabilizing. Those big groups don't like being near one another in space. Okay, so now we've gone through and I've said, all right, that's first. We've got a second place winner here, second place winner here. It's pretty good. All right, now let's look at the various eclipse conformations. All right, we're looking between B, F, and D. Which one do you think is going to be far and away the least stable? D. We've got two methyl groups completely overlapping, so I'm just going to immediately write least stable. It's the loser, but it still gets the rainbow pen. All right, between B and F, which one's more stable, or is it a tie? Or a tie, right? So I would say third, third, and so on. So we've immediately ordered them in terms of their relative stability just by doing simple conformational analysis with Newman projections. All right, we do have a few more nomenclature or naming systems we have to talk about. If we look at conformation A, where it's staggered like that, that's referred to as anti-periplanar, meaning the methyl groups are anti to one another, so we want to indicate that. And then if you go through, the other one that has a unique name is actually D. You see how it's eclipsed, but now those two groups, instead of anti, they're on the same face of one another. This is called syn periplanar. Because now those two methyl groups are aligned, but they're on the same face, they're overlapping with one another as opposed to anti. So you might occasionally see those terms thrown out as well. All right, so now what we're going to do is make a big graph showing the potential energy for each of these rotational clips. So I'm just going to draw this down here. And instead of drawing out the full structure, I'm just going to use the letters that we coded them as, right? All right, we said compound A was going to be the most stable, right? So I'm going to put A down here, relatively stable, so low potential energy, and eventually we're going to get back to A. All right, what was the highest potential energy? D. If we go back up and we look at it, D was definitely. The other thing too is D is about halfway between getting all the way back to A. Do you see that? So we go 2 clicks and then we get to D, and then 2 clicks further and then we can go back to A. So I'm going to put D in the middle at some really high energy right here. Makes sense? And then if we think about A going to B, we're going to a really high energy, and then we're going back down to second most stable. So I'm going to put this up here. So I'd say B and then C. So can you see? Let's zoom out a bit. We said A is definitely the most stable. We're going to have to apply energy to get to B. That's our our eclipse conformation. And then when we go to C, we drop back down, but C is higher energy than A. And then we're going to go back up to D like that. And then we said down here that E is actually the same energy level as C. And then last but not least, we go to F. That's right here. And then back down to A. Some people last year referred to this as the figurative middle finger from butane. Take it however you want. But it's important to remember that D is really high in energy. Not all of these energetic barriers are going to be the same, right? So we do have to analyze the potential energy anytime we're doing these rotations. It is important, too, to actually ask yourself how much energy is required to go over all of these humps. So I pulled up some values. This hump, going from A to conformation B, so we're going from staggered to eclipsed, is about 3.6 kcals per mole. People might be thinking, oh, wow, yeah, I have no idea how to reference that. And then going from A all the way to D is about 6 kcals per mole. Like I said, these numbers are completely useless unless you have some sort of internal reference point, right? So what I always tell students to remember is that room temperature, we have heat in the room, right? Heat can be useful towards rotating bonds. The heat in a normal room temperature situation is about 20 kcals per mole. So room temp allows molecules to rotate if the barrier is below 20 kcals per mole. All right, so if we think about this molecule, butane, will it rotate freely? Yeah, definitely. It's got more than enough energy. It's happy to spin around in space like helicopter blades, just twisting wildly. Yep.
So if for instance A to B was below 20, but A to D was above 20, would it go between like A, B, C, and then back C, D, A?
Yeah, so there was a question, what if you have one barrier that's above 20? You can often get stuck in these wells where it can't cross completely in a 360. It can maybe only go back and forth like a seesaw almost. Does that make sense? If you think about this, though, what happens if you, let's say, cool this down in liquid helium that is very, very cold, close to absolute zero? Will it rotate? No. So if you cool molecules down, you take away the energy, they don't actually have enough to rotate freely past those single bonds. There's too much energetic rubbing of those methyl groups to allow that to happen. Yep.
So how does these kcals factor into nutritional kcals? Same, different?
So if you think about kcals in food, that's the amount of energy you get from combusting something, right? In this case, we're not looking at combustion. We're just saying the amount of energy per mole in order to allow for this to happen. Yeah.
So the molecule would never actually go from exactly A to D. So that threshold of 6, is that not necessarily like prohibitory? What if you had like 5 kcals per mole?
Yeah, so the question was about, all right, we can't go directly from A to D. We have to go A to B to C and then to D. But ultimately, that net barrier is still way below 20 kcals per mole. So this has no problem rotating past all of those hurdles. If you do have really, really big groups, let's say you have terp-butyl groups coming off of both sides, then maybe it will be close to 20 kcals per mole and won't rotate as freely. There's a bunch of cool experiments you can do with these using spectroscopy and actually cool them down and heat them up and investigate how they respond in a spectrometer. And that's actually how they're able to measure these rotational barriers. It gets into more physical organic chemistry or just straight physical chemistry, though. So kind of crossover between physics and chemistry. All right, does this make more sense now? All right, I've got a harder one. All right, I will tell you that problems like this are almost guaranteed to be on the first exam. I'm going to draw in some of these hydrogens just to help. All right, let's try to name this first of all. What would this molecule be named? So longest carbon chain is that backbone that's zigging and zagging, right? So 6 carbons long. The methyl group looks like it's coming off of carbon 3. So I'd say, all right, this is 3-methyl-hexane, right? Because we'd say 1, 2, 3, 4, 5, 6. That's the longest carbon backbone. Methyl group's coming off of carbon 3. All right, so what I want you to do is to draw all 3 staggered conformations, not the eclipse. Oh. And I want you to look down the 3-4 bond. All right, so I'll give you a minute to draw all of these potential conformations. But like I said, I don't know why this helps me, but I just imagine my eyeball looking straight down these. And then once you've drawn all 3 possible staggered conformations, what I want you to do is to determine which one's the most stable, second most stable, and third most stable. And I will give you a hint too for abbreviations. If you're looking down that bond, what would this group be called? Well, specifically, it's 2 carbons. What do we call a 2-carbon substituent? Ethyl. So I would just abbreviate this ET. It'll make your paper a lot neater. Same thing with this one. That's coming off of carbon 3. So we can abbreviate that ET. So use abbreviations as needed to help simplify your drawings. And then conversely, you could abbreviate this one ME if you want to for a methyl group. While you're working on that, I'm going to just draw a skeleton structure. Oh, that looks terrible. All right, who needs a little bit more time on this one? Okay. All right, let's try to do some of this together. So imagine I've got my right eyeball. I'm looking down carbon 3 to 4. What's sticking straight up? An ethyl group. So I'm going to immediately say the ethyl group in that original conformation as drawn, the ethyl group is sticking straight up from my eyeball. All right, and then I think about it. All right, my methyl group is a wedge, so it's coming out of the page. Will that be to the right or left bottom? On the right bottom. And the hydrogen coming off of carbon 3 is a dash, so that'll go to the left. It's important to remember, too, that a wedge and a dash doesn't necessarily mean one's always going to the right or one's going to the left. You have to imagine your eyeball looking down that bond and then ask yourself, all right, that's a wedge. I'm going to swing it around. That means it's going to my right, not my left. Okay? So we've got our front carbon taken care of. If we look at our back carbon, it's a little bit easier. The two groups sticking straight up are the hydrogens. So I'll go ahead and say those are sticking straight up. And then what's sticking straight down? An ethyl group. All right, so just like I said before, when you're doing these rotations, keep either the front carbon static or the back carbon static. You don't want to move both at the same time. So let's just keep the front carbon static. So I'm going to copy everything over. The front carbon is staying put. I'm only rotating the back carbon. All right, so if I'm moving the back carbon, that means that this hydrogen is going to get moved down here. This ethyl group is going to get moved up here, and that hydrogen is going to get moved over there, right? So the ethyl group is now going to rotate over to this position. The two hydrogens are going to be left over. And then we can take this ethyl group, move it over here. This hydrogen, move it over here. This hydrogen, rotate it over there. So another 120-degree twist. That means our ethyl group must now be on this side, and the hydrogens left over here and here. All right, I'm going to erase this. What I want you to do now is to ask yourself, all right, which of these is the most stable? Second most stable, third most stable, and then check with your neighbor and see if you agree. So think about it as A, B, and C. Determine is A most stable, B most stable, C most stable, and so on. All right, let's see a show of hands. Who thinks A is the most stable? That's good. I think A is the most stable too. So this is most stable. Why is that though? Okay, I heard back here, ethyl groups are the largest substituents coming off those carbon bonds, and they're the furthest away from one another. I'd say that's a super valid thing. Are there any Gauss interactions? So Gauss interaction is basically between any two non-hydrogen groups. Yeah. Right there. So we do have a Gauss interaction in this one, but still the ethyl groups are further away from one another, so that's winning. All right, if we look at B, we've got some Gauss interactions too. So my question is, well, why is B less stable than A if they both have Gauss interactions? Yeah, ethyl groups are much bigger than methyl groups. So two ethyl groups clashing with one another is going to have a much more destabilizing effect than a methyl group and an ethyl group clashing with one another. All right, so that one, yeah, not so great. Let's look at C. Are there any Gauss interactions? Double Gauss. We got a Gauss interaction here, Gauss interaction right there. Immediately that means that C must be the least stable. And this one's going to be somewhere in the middle. So whenever you're looking at these, you always want to look at Gauss interactions and then analyze, all right, which Gauss interactions are the worst? Yep.
So is it possible for, if there's like multiple Gauss interactions, for it to be less stable than eclipse?
So the question was, if you've got a bunch of Gauss interactions, is it possible to be less stable than an eclipsed? I don't believe so. However, I'm sure there are exceptions to that. I would have to look it up. Yeah, good question. All right. So questions like this could show up on the exam. In fact, they will show up on the exam. So make sure you practice them. It is hard, especially if you struggle with three-dimensional imagination. That's where physically building something with your model kit and rotating it can actually help, and then physically look down the bond, rotate the front one, or rotate the back one. So don't be afraid of using your model kit. Make sense? Okay, so we're going to change gears a little bit and start talking about cyclic ring systems. And specifically, we're going to look at cyclohexane. So I'm going to say there are many ways to draw a cyclohexane. Okay, the first and easiest one is with bond line notation. And if we think about bond line notation, hexane we know is 6 carbons. The cyclo in the name means it's a ring system. So a 6-carbon ring system, easy peasy, right? All right, the next one's a little bit harder. If we look at this, it doesn't really give you any three-dimensional imagery of what's going on in space. So what we could do is a double Newman projection. So let's say we're looking down both of those carbon-carbon bonds. So let's think about the one on the left. We know that they're all sp3 hybridized carbons. They're going to be about 109.5 degrees away. So we'd have a hydrogen sticking up like that. And then in the back, we'd have maybe a hydrogen sticking out and down, and then another group sticking out like that. So that's our left carbon. And then it connects to our right carbon. It looks like this. Kind of confusing, right? But think about it this way. This red dot is a carbon connection point. It's the same carbon dot right there. And in this case, it's puckered down. So I'd say CH2 is puckered down. And then in the back, I'd say, well, we've got this green carbon that must be puckered up. To be perfectly honest, these Newman projections are a royal pain to draw. Most chemists don't do these because they're so challenging to draw. Instead, in order to show the three-dimensional representation, we use what's referred to as a chair structure. So let's take a look at a chair. And the chairs arguably aren't even easier to draw, but they do a better job of describing the three-dimensional space. And don't worry, I'll show you how to draw these better. Everyone's like, what are you doing? Stop it. Just stop it right now. Let's see. All right. So super easy peasy chair structure, right? Makes perfect sense. These are really hard to draw. But the easiest way to think of, right, is 2D is looking down like this. And then Newman projection, we're looking down like that. You see how one's puckered up, one's puckered down. Still not super easy to see. And then a chair is more like a side on. So to show this a bit better, because I know it's hard to see mine, we've got a video. So that's 2D to Newman to chair. Let's do it again. 2D. That's not my house. Newman to chair. We'll do it one more time. 2D to Newman to chair. Right? It makes perfect sense. So, like I said, bond line notation, in terms of easiness to draw, far and away the winner. Newman, I don't know about that. Chair gives you a lot of three-dimensional information. It's more the side-on view of a cyclohexane molecule. All right, I think what we're going to do is cut off there today. Tomorrow when you come in, please bring your model kit. And when you come, already have cyclohexane pre-made, and I'll show you how to do something called a chair flip with your model kit. So make sure you come tomorrow prepared with cyclohexane.